SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be revisiting the nonlinear equation of motion of the aircraft rotational dynamics or attitude dynamics. Then we'll apply the linearization technique to the system based on the assumption of small angular displacement, and the inertia matrix is assumed to be only has the principal moment of inertia. After applying this assumption, we can come up with the linear form which relates between the angular displacement and the applied torque and moment or moments and disturbance acting on the system. This equation will help us to find the transfer function of the attitude dynamics of the aircraft. In this lecture, we'll be discussing how we can design autopilot of an aircraft. So we'll be starting with the attitude motion of the aircraft, how we can control the orientation of the body. So let's assume we have aircraft system, and we would like to control the orientation of the body. Suppose this is my aircraft, and these are the axes, for example, X, Y, and Z. And would like to maintain the orientation of this body with respect to some frame, maybe inertial frame. And so here, since we are going to discuss on orientation control, so mostly we'll be using the moment equation and kinematic equation. So we'll be having this equation very soon. And we would like to control the orientation of the body, phi, theta, and psi. So for controlling the orientation, we need to apply some control to the system. So we'll have some control U1, U2, U3. So these control going to be control theta, phi, psi, respectively 3 angles. So 3 controls we'll be using for this system. This is the controller. So controller, we need to design in such a way that we will get our desired response, phi theta psi. So this is the objective of this lecture. And next few lectures will be involving in this part how we can control the orientation of the aircraft and how we can design autopilot, how we can come up with the logic to maintain the desired accuracy of the system. So in this motivation we'll be moving. Now let's write the moment equation. We are not going to derive how the equation came because that is a long part. In this course, mostly we'll be designing the control. So let me write the equation of motion of the aircraft, the moment equation. The moment equation of the aircraft we can write L is the total moment acting to control the pitch axis of the aircraft. So this is P dot Ix minus R dot Ixz plus QR IZIOI and minus Ixz PQ. And L is the total moment acting on the x-axis, and M is the total moment acting along the y-axis, and Q dot IY plus RP Ix Iz plus Ixz p square r square, and n is the total moment acting along the z-axis. Ixc p dot plus Iz r dot plus pq Iy minus Ix plus Ixz qr. So here P is the roll rate and Q is the, so let me define here, P, Q, R rates of X, Y, Z, and Ix, Iy, Iz principal moment of inertia along X, Y, Z, and Lmn total moments acting along X, Y, and Z. So this total moment can be your torque moment and also disturbance, any other part of in the system. So the torque is basically also disturbance, but this is the favorable disturbance. This is going to help our system to regulate to our desired orientation. And here Ix Z off diagonal term in the moment of inertia matrix. I think we are done with the terms. Now, this is, let me define, this is equation number 1. And also we need the kinematic equation because we are going to control the orientation of the body. So also we need to consider the kinematic equation. And the kinematic equation, we can write phi dot P plus Q sine phi tan theta plus R cos phi tan theta dot equal to Q cos phi minus R sine phi and psi dot equal to Q sec theta sine phi plus R sec theta cos psi. And this is the kinematic equation. Let's define this equation number 2. So here theta phi psi, this is the angle of the axis. So now we'll be using this equation, how we can design autopilot for this dynamic system. So here, as I said, the external moment. Okay, let me say something more on this equation. So these equations are highly nonlinear equation. This equation are highly nonlinear because of the coupling terms exist. Suppose here p square r square, this is the square term or coupling term exist. And also in the kinematic equation, the q sine phi, tan theta, r cos phi, tan theta, these are the coupling terms, and due to which the system become nonlinear. So system will not follow the principle of superposition. Now, the external moments Lmn has two components. has two components. As I said, it can have the torque as well as the perturbations. L, M, N be the control moment, which is given by the controller, and L disk, M disk, and N disk be the disturbance or perturbations into the system. Now, based on this, we can write L equal to, we can write L plus L disk and small m plus m disk. This is small m. This is small m disk, and your n equal to n plus n disk. And also, let's assume the moment of inertia has only the principal moments of inertia. It means we are assuming the off-diagonal terms to be zero. So we are assuming as ix 0, 0, 0, iy 0, 0, 0, ic 0. Where off-diagonal terms are assumed to be 0. Now, also we'll have another assumption. Let's assume the small angle and rates. So also let's assume the small angles and rates approximation. So in this case, for small angle, we can write sine phi equal to phi, equivalent to phi, and cos phi equivalent to 1, and sine theta equivalent to theta, and cos theta equivalent to 1, sine psi equivalent to psi, and cos psi equivalent to 1. In this condition, the kinetic equation based on the above assumption, the equation number 2, the kinetic equation yields phi dot equal to p plus q phi theta plus r theta, and theta dot we can write q minus r phi, and psi dot we can write q phi plus r. The small angle and rate assumption also allow us to neglect product of between the angles and angular rates. We can write also due to the small angle and rate assumption, the products between angles and angular rates can be neglected. So the terms we can neglect: phi theta, r theta, r phi, and q phi. These terms we can neglect in equation 3. Based on this assumption, these assumptions, equation 3 can be written as, right, phi dot equal to p and theta dot equal to q and psi dot equal to r. So if you notice, this equation come up some nice form, but we need more treatment on the other moment equation also. So let's write, this is equation number 4. Now, for small angle approximation, again, for small angles and rates approximations, we can write the equation number 1 can be written as, we can write L plus LDs equal to P dot Ix. Because other term we can ignore in our moment equation. These are the terms we can, because Ix z assumed to be 0 in the off-diagonal terms, and these term we can neglect because of the coupling between the small angle and rates, because this is the rate, this is the coupling, this is the multiplication of the terms, angular rates terms, and which are assumed to be 0. So we can neglect these terms. So from the first equation, in moment equation, we can write this expression, and this is how it is coming. That is also it's clear, because we have assumed that the total moment acting in the axis L capital plus L dis, L is the disturbance and L is the moment, torque moment, which is given by the controller. And similarly, for the y and z direction, we can write m plus m dis equal to q dot iy and n plus n dis equal to r dot ic. From this expression, we can further write, let me define this equation number 5. If you notice, our from equation 4, phi dot equal to p, right? This expression. So p dot we can write phi double dot. So in place of p dot, we can write phi double dot. And similarly, in place of q dot, we can write theta double dot. In place of r dot, we can write psi double dot. So now, from equation, using equations 4 and 5, we can write ix ix phi double dot equal to L plus LDs and IY theta double dot equal to M plus MDs and IC psi double dot equal to N plus NDs. This equation we can write equation number 6. Now, if you notice in this equation, 6, each equation are decoupled from each other and they have the same form. So conclusion from equation 6, from equation 6, we can write equations are decoupled and have the same form. Therefore, if you can take one equation and if you can design the control for that particular equation, then it will be the same technique also you can apply for the all other equations. So let's take one equation because the concept will be same for other equation as well. So if you consider, for example, this equation, and if you can design the control for this equation, the same concept we can apply for the rest of the systems, phi double dot and psi double dot. So let's consider only one axis at a time to be controlled. And let's consider theta of t to be controlled. So in this direction, let's assume Iy theta double dot equal to m plus mds. This is the equation we are going to consider for designing control for it. For this particular equation, we'll be spending around 5 to 6 lectures how we can design a controller to control theta. For this is instead of IY, we can let's write I only. This same, right? IY. Just for simplification, let's write I I theta dot equal to m plus m this. Now, this is our main equation to be regulated with design control. This is the equation we would like to regulate. The quantity here, the quantity that we are interested to control is the attitude, same thing, orientation, angle, theta. Theta is the only angle we want to design the control. Would like to control, which is generally called the planned output. And in that case, we can write the planned output y of t, we can write theta of t. So just for, for easy access of the systems. So instead of writing theta t, would like to control theta. So that's why we are writing this y of t. Y of t is the variable to be controlled. And the quantity, that can be used to affect the attitude is the control torque, which is generally the control input or plant input, and which can be labeled as ut equal to m. The same thing, so we are trying to connect to the control perspective. Y of t equal to theta t, u of t equal to m. So if you write in block diagram form, so this is our plant, which is basically I theta double dot equal to m plus m dis. So here, this is the total moment coming to the system, m plus m dis. So here basically I have a summing point, which is m dis coming from the external perturbations from the outside, it may be disturbance, and it is coming from the controller, which is AU equal to m. And the output from this system, we can write y of t equal to theta of t. So this is how we can design in block diagram form. Now we have to design a controller U, which will regulate the system and which will help us to maintain our desired attitude of the system. So now let me write a note here. Why, for this particular system, why we have to assume the initial condition 0. So assumption on initial conditions. So here, first is we'll be assuming the initial condition to be 0. We are not interested in the response of the output to non-zero initial conditions. This is the first assumption, and that is a valid also. That is we already discussed why we should not consider. And second is, even if you consider initial condition non-zero, this non-zero initial condition will disappear to 0 provided the control system is designed designed to be asymptotically stabilizing. So this is the another condition why we should not, even if we have a zero initial condition, non-zero initial condition, it will be zero if the system is the control is asymptotically stabilized. Third, in this particular contour synthesis, we are interested in how the system responds to an input, which will affect how the control system to be designed. That is our main purpose. So that's why we will set the initial condition. Therefore, we assume the initial conditions to be zero. The other reason also we have discussed in the previous lecture why you should not consider the initial conditions to be zero, since we will be dealing with the causal system, which is if the time is less than zero, then the initial condition will assume to be zero. So this thing already you have discussed extensively. Next topic here will continue from the next lecture, how we'll come up with the transfer function for this particular system, and we'll try to connect with the controls. Thank you.